Today's discussion is about lanthanides and actinides. What are these lanthanides and actinides? When we check the periodic table, we find that there are 14 different elements lying in between the group 3 and group 4 in the fifth series and the sixth series. You find that the 14 elements lying in between lanthanum and hafnium, in between the third group and the fourth group in the sixth period, that is known as lanthanides, because here they have the similarity with that of lanthanum. The outermost configuration is the same. The inner penultimate shells, that is the f orbitals, are being progressively filled here. Starts from cerium to lutetium. Here the f orbitals are being filled up. Coming to the next one, that is actinides. These are 14 elements lying in between actinium and rutherfordium, starting from thorium to lawrencium. This lies in between the third and the fourth group in the seventh period. Now we will see what are the consequences of lanthanide contraction. Now when we are checking the different groups here, we have learned that when we are moving down in a group, the size of the atom keeps on increasing, and when we move across in a period, the size of the atom keeps on decreasing. When we check the D block elements, it is found to be almost the same, but there are a few variations occurring here. In the period-wise distribution, when we check the 3D series, on analysis of the 3D series, you find that from scandium to chromium, the size of the atom keeps on decreasing. But from manganese to copper, the size is remaining the same, and from copper to zinc the size slightly increases. Why there is a change in the ionic and atomic sizes here? It is due to two factors. One factor is known as the effective nuclear charge, and the other one is the screening effect. Now when we are filling up the electrons in the d orbitals, that is in d block, you find that with every increase in atomic number, the electron enters the d orbital, which is the penultimate shell, and d orbitals are having poor shielding effect. With the result, what happens is, with increase in atomic number, the number of protons increases, nuclear charge is increasing, and the electrons are entering the d orbitals, which are having poor shielding effect. With the result, what happens is, the growing nucleus will have more pull towards the outermost orbitals, and as a result the size keeps on decreasing. So this is true from scandium to chromium, because the effective nuclear charge is more compared to the shielding effect. Now when we check the shielding effect and effective nuclear charge of manganese to the elements up to copper, you find that up to nickel, you find that the sizes are one and the same, because the effective nuclear charge and the screening effect are almost the same. Coming from copper to zinc, you find that the effective nuclear charge is less than that of the screening effect. With the result, the nucleus cannot pull the electrons effectively towards it, and as a result the size keeps on increasing. Consequences of lanthanide contraction. Due to lanthanide contraction, all the lanthanides are having almost similar sizes, due to which the separation of lanthanides are very difficult. The second point is basic nature of the lanthanide hydroxides usually decreases from left to right. We'll see that lanthanides are written as Ln3+. So when it forms hydroxide, it forms LNOH thrice. So you find that the starting element is lanthanum with LaOH thrice, and the ending element is lutetium with LuOH thrice. On comparing the sizes of the cations, you find that lutetium is much smaller in size, due to which you find that it will have more covalent character due to Fajan's rule. So with the result, you find that basic character will be more for lanthanum hydroxide compared to that of lutetium hydroxide. Now, another consequence of lanthanide contraction is the density of the hydroxides. You find that when we are moving from left to right, the size of the atoms are decreasing continuously. So with the result, density of the atoms are more, because more and more atoms can be packed in a limited space. Coming to chemical reactions. When you take the lanthanides, the common oxidation state of lanthanides are given as +3. So these lanthanides can undergo a variety of chemical reaction. When it burns in oxygen, you find that it forms lanthanum oxides. So lanthanide oxides are given the formula Ln twice O3. These are called the oxides. When it reacts with sulfur, that is heating in the presence of sulfur, it forms the sulfides. You know the formula will be Ln S. S is having -2, so it will be Ln2S3. So this is the formula for sulfide. Now when it reacts with nitrogen, it forms the compounds known as nitrides. Nitrides are formed, and it will have the formula Ln N, because this is +3 and N is also -3. So Ln N, this is the formula of the nitride. When it reacts with carbon, when heating is done at 2773 Kelvin, 2773 Kelvin, you find that it forms the carbides. Carbides are formed with the formula LnC2. Coming to the reaction with water. On treating it with water, you get lanthanum hydroxides with the formula LNOH thrice plus hydrogen. When it reacts with acid, on reacting it with acid, it forms the corresponding salt, liberating hydrogen. And finally, the last reaction is reaction with halogens, when it forms LNX3, and the compounds are known as halides. So in all the reactions that we have mentioned here, lanthanides will show +3 oxidation state. If you check the periodic table, you find that an element with Ln is not there. This is the general representation of all the lanthanides.